Welcome to our deep dive today. We're going to be exploring the life and work of Werner Heisenberg,
Yeah,
a
yes.
really central figure in the development of quantum mechanics.
Absolutely, yeah. It's a fascinating story.
Yeah, it really is.
Full of these breakthroughs,
Yeah.
but also personal struggles
Yeah.
and even some political controversies.
Exactly.
Yeah.
So what makes this deep dive extra intriguing
Yeah.
is that we have excerpts from a Heisenberg biography to actually trace his intellectual journey.
Yeah.
So not only will we learn about the science,
Right.
but we'll get like a glimpse into Heisenberg's mind
Yeah.
as he's developing these ideas,
Exactly.
and also the scientific landscape
Yeah.
of the early 20th century.
It was a pretty amazing time to be a physicist.
Yeah, really a period of incredible change and upheaval.
Absolutely.
So our mission today,
Our mission, we choose to accept it.
exactly, is to understand Heisenberg's key contributions, the core concepts of quantum mechanics,
Yeah.
and how those revolutionized our understanding of the universe.
It's a journey
Yeah.
that takes us from the,
Yeah.
seemingly solid ground of classical physics
Yeah.
to the mind-boggling world of quantum uncertainty.
Right.
It's going to be fun.
Absolutely.
So,
To understand the impact of Heisenberg's work, we need to start with kind of a snapshot of physics in the late 19th century.
okay.
And it was a time of incredible optimism and
Almost like a sense of completion.
yeah, they felt like they had it all figured out.
Almost like physics was done.
Right, like, we've got this.
Yeah, just wrap it up.
Back it up, go home.
Put a bow on it.
Yeah, think about the discovery of Neptune in 1846.
Yeah.
Astronomers found it by noticing these slight wobbles
Little wobble.
in Uranus's orbit.
You ran it.
And they used Newton's laws to predict where this new planet should be. And
Yeah.
boom, there it was.
There it is.
It's like they predicted a planet into existence.
It's like magic, but it's not.
Right, it's the power of Newtonian mechanics,
You did-
which had successfully explained the motion of planets.
Yeah, the swing of pendulums.
Right, all these different phenomena.
Countless other phenomena.
So they had every reason to believe that their framework was essentially complete.
It's just Newton.
That's all you need.
Just add Newton.
Yeah, and then Maxwell's equations were published in 1873.
Oh, yeah. Those are good.
Really seemed to solidify this confidence
Absolutely.
because they unified electricity and magnetism.
Yeah, brought them together
Yeah.
into one beautiful framework,
Yeah, and predicted the existence of electromagnetic waves.
which is pretty amazing.
Yeah.
I mean, who would have thought that electricity and magnetism were connected to light?
Right.
It's mind-blowing.
Yeah. And then just a few years later, Hertz confirmed these predictions by producing and detecting these waves in the lab.
Exactly.
So it's like, okay, well,
So we're good, right?
we're done. Let's go home.
Let's go home. But
The universe loves to surprise us.
always throwing curveballs.
Always throwing those curveballs. And right at the turn of the 20th century, this series of unexpected discoveries kind of opened a crack in this seemingly solid foundation of physics.
A little crack that turns into
Yeah, this chasm.
a giant chasm.
It started with things like X-rays in 1895,
Yeah, X-rays.
radioactivity in 1896.
That one was a big one.
Yeah, the discovery of the electron in 1897.
So many things happening.
These phenomena simply couldn't be explained by classical physics.
Nope. They hinted at something deeper.
Yeah.
Something more fundamental.
A realm where the familiar laws no longer held sway.
Yeah, it's like we stepped into a new world.
Exactly.
The quantum realm.
And one of the biggest puzzles that emerged was something called black body radiation.
Ah,
So imagine an object
okay.
that absorbs all radiation,
All of it.
kind of like a perfect absorber of light and heat.
Yeah, like a black hole, but not quite.
Exactly. So when you heat this object,
Okay.
it starts to glow.
Right.
It emits radiation across a spectrum of colors.
Yeah.
Now, classical physics predicted that the intensity of this emitted radiation would increase infinitely at high frequencies.
Okay, so brighter and brighter and brighter forever.
And beyond.
Which obviously doesn't make sense.
Doesn't work that way.
It was dubbed the ultraviolet catastrophe.
Oh, yeah. It's a good name.
It's a dramatic name
Very dramatic.
for a very dramatic problem.
For a very big problem.
And it was Max Planck in 1900
Oh, Max Planck.
who offered a solution that would change the course of physics.
He did?
He proposed that energy at this microscopic level
Okay.
wasn't continuous, but came in discrete packets, which he called quanta.
Quanta.
So it's like instead of a smooth ramp, it's like a staircase.
Those little steps.
You can only go up in these specific increments.
It's quantized.
It's quantized.
Mind-blowing.
Planck himself considered this idea like a mathematical trick.
Yeah, a bit of a fudge.
Yeah, a desperate measure to fit the data.
Right.
He wasn't quite sure what to make of it.
A bit of a kludge, if you will. But Einstein, in 1905, took this concept and ran with it.
He said, I like this, let's go.
He used the idea of light quanta, later called photons,
to
explain the photoelectric effect.
Oh, yes.
Where shining light on a metal could eject electrons.
That's a weird one.
Yeah, classical physics could not account for this, but Einstein showed that light was acting like a particle?
A particle?
A tiny packet of energy.
Yeah.
This was a major departure from the wave theory of light.
Huge departure.
That had been accepted for centuries.
Yeah, we thought we had light figured out.
But now we have this wave-particle duality.
It's like light is playing tricks on us.
Right. So now we have this backdrop of crumbling classical physics.
Right. The foundation is shaky.
These tantalizing hints of a new quantum reality.
We're on the verge of a revolution.
And into this world enters Werner Heisenberg.
Our hero.
A young man with a deep fascination for the mysteries of the atom.
He was always asking questions.
Yeah.
Poking and prodding.
And Heisenberg wasn't initially drawn to atoms just for scientific reasons.
Right.
He had kind of a philosophical bent.
Yeah, he was a deep thinker.
He questioned the existing models of the atom, which he found too superficial, too reliant on visual representations.
Yeah, he wanted something more.
He wanted a deeper, more fundamental understanding of atomic structure.
He wanted to know what was really going on down there.
Exactly, and he had a strong interest in mathematics.
Right.
But he ended up studying physics.
Of course he did.
Under Arnold Sommerfeld.
Sommerfeld, a great physicist.
At the University of Munich, a hub of atomic research.
Yeah, Munich was the place to be.
At the time, the physics world was abuzz with trying to model the atom to explain the intricate patterns observed in atomic spectra.
Atomic spectra, those unique fingerprints of light emitted by different elements.
Like each element had its own barcode.
Exactly, and those barcodes held the secrets to the atom.
The planetary model with electrons orbiting the nucleus like planets around the sun was tempting.
Right, it's a nice picture.
It's a nice picture, but it just didn't work.
It had some problems.
Yeah.
Big problems.
According to classical electromagnetism, an electron orbiting the nucleus should constantly radiate energy.
Lose energy.
And quickly spiral into the nucleus.
Yeah, atoms should collapse.
Yeah.
But clearly atoms weren't doing that.
Atoms are stable.
They're doing just fine.
Then in 1913, Niels Bohr, the Danish physicist, proposed this radical new model.
It was a game changer.
Yeah. He suggested that electrons could only occupy specific stable orbits or stationary states where they wouldn't radiate energy.
So they're just hanging out in these specific orbits.
Yeah.
Not radiating energy.
And only when an electron jumped between these orbits would it emit or absorb light.
Like quantum leaps.
Quantum jumps.
Yeah.
Which explained the discrete lines observed in atomic spectra.
It was a brilliant insight.
Yeah, Bohr's model, though it had its limitations, was a huge step forward.
Absolutely.
It explained the spectrum of hydrogen, the simplest atom, with remarkable accuracy.
It was a triumph.
Sommerfeld, Heisenberg's mentor, refined Bohr's model, further introducing elliptical orbits and a new quantum number to account for the fine structure observed in atomic spectra.
Yeah, Sommerfeld was a master of atomic spectroscopy.
But even with these refinements, the theoretical foundation remained shaky.
It was like building a house on sand.
Yeah, it was becoming increasingly clear that a truly new framework was needed.
A revolution was brewing.
And even as a student,
Young Heisenberg?
Heisenberg was already pushing the boundaries.
He was always a bit of a rebel.
Sommerfeld, recognizing his talent, challenged him with a particularly tough problem related to the Zeeman effect.
The Zeeman effect.
This describes the splitting of spectral lines when atoms are placed in a magnetic field.
It's like the magnetic field is perturbing the atom.
Yeah.
Causing its energy levels to split.
Heisenberg, always up for a challenge, came up with a model that used half-integer quantum numbers to explain the observed data.
Half-integer quantum numbers, that was bold.
Yeah.
There was no theoretical justification for that at the time.
It went against the conventional understanding of how quantum numbers worked.
But Heisenberg's model, despite its theoretical shortcomings, did a remarkable job of reproducing the experimental results.
So it worked.
It worked.
But nobody really knew why.
It was a mystery.
It showed his willingness to challenge conventions and push the boundaries of theory.
Yeah, he wasn't afraid to break the rules.
Even if it meant venturing into uncharted mathematical territory.
He was a pioneer.
Sommerfeld, though impressed, admitted that the deeper meaning of Heisenberg's model remained obscure.
It was a puzzle,
It felt like they were assembling a jigsaw puzzle with missing pieces.
and those missing pieces were crucial.
This sense of incompleteness of a puzzle waiting to be solved would drive Heisenberg's work in the years to come.
It was a driving force.
It was becoming increasingly apparent that the existing models were becoming too complex, too ad hoc.
Yeah, they were like patchwork quilts.
They were lacking a fundamental theoretical basis.
They're missing a solid foundation.
This growing crisis in atomic physics set the stage for Heisenberg's groundbreaking work.
The stage was set.
After completing his doctorate, he went to work with Max Born in Göttingen,
Max Born, a brilliant mathematician and physicist.
who advocated for a more rigorous mathematical approach to atomic theory.
Yeah, Born was all about the math.
Heisenberg, initially skeptical of Born's methods,
He thought it was too abstract.
found himself immersed in the world of advanced mechanics.
It was a whole new world.
A far cry from the more intuitive approach he had learned under Sommerfeld.
Yeah, it was a big adjustment.
But this exposure to advanced mathematics would prove invaluable.
It would be the key to his breakthrough.
Heisenberg was grappling with the limitations of his own Atomrumpf model,
The Atomrumpf model.
which, despite some success in explaining certain spectral features, remained fundamentally flawed.
It was a dead end.
He began to realize that the focus on visualizing electron orbits, on creating these classical pictures of what was happening inside the atom, was leading them astray.
Yeah, those pictures were misleading.
It was time for a radical departure.
A paradigm shift.
A shift in perspective that would change the very language of physics.
And that's where we'll pick up next time.
Yeah, we'll see what happens next.
Stay tuned.
It's going to be exciting.
It's going to be revolutionary. Welcome back to our deep dive into the quantum world of Werner Heisenberg. When we left off, Heisenberg was working with Max Born, immersed in the world of advanced mechanics.
Right.
It was a time of intense intellectual ferment, and things were about to take a truly revolutionary turn.
You mentioned that Heisenberg began to question the very idea of visualizing electron orbits.
Yeah.
What led him to this radical shift in thinking?
Well, he realized that focusing on these classical pictures was hindering their progress.
Okay.
I mean, after all, no one had ever actually seen an electron orbit.
Right.
It was a theoretical construct based on our everyday experience with larger objects like planets.
Yeah.
But at the atomic level, things were clearly different.
So he decided to abandon this visual approach.
Precisely. He decided to focus solely on what could be observed and measured.
Okay.
Things like the frequencies and intensities of spectral lines, the unique fingerprints of light emitted by atoms.
So it's almost like saying, let's stop worrying about what's happening inside the atom,
Right.
which we can't directly observe,
Exactly.
and just focus on the information the atom itself is giving us.
That's it. Heisenberg focused on the mathematical relationships between these observable quantities.
Okay.
And this led him to develop a new system of mechanics based on matrices.
Matrices.
Yeah, mathematical arrays of numbers that could represent these relationships.
Okay, I'm not sure I fully understand what a matrix is, but go on.
Well, don't worry too much about the mathematical details for now.
Okay.
The important point is that Heisenberg found a way to represent the observable properties of atoms using these mathematical objects called matrices.
Okay, so this was the birth of matrix mechanics, right?
It was.
But wasn't he working with Born at the time?
He was.
What was Born's role in all of this?
Well, Born was initially puzzled by Heisenberg's strange new theory.
Yeah.
It was a completely different way of thinking about mechanics.
Right.
But he quickly recognized the brilliance of Heisenberg's ideas
Okay.
and helped develop the formal mathematical structure of matrix mechanics.
And those a true collaboration.
Absolutely.
Right.
Born and another physicist, Pascual Jordan,
Okay.
worked closely with Heisenberg to refine and expand the mathematical framework of matrix mechanics.
Okay.
It was a team effort,
Right.
but it was Heisenberg's bold vision that paved the way.
Okay, so this matrix mechanics based on these strange non-commuting matrices could actually describe atomic phenomena.
It could. And not only could it describe them,
Yeah.
it did so with remarkable accuracy.
Wow.
It successfully predicted the frequencies of spectral lines and other atomic properties that had puzzled physicists for years.
So it worked.
It worked beautifully.
But this was a radical departure from classical physics.
Absolutely.
It wasn't just a tweak to the existing theories. Yeah. It was a completely new way of thinking about mechanics.
It was a revolution.
A way that embraced uncertainty at its core.
Right.
This brings us to one of the most profound
And dare I say mind-boggling.
aspects of quantum mechanics.
Indeed.
Wave-particle duality.
Yes.
I remember you mentioned this earlier.
I did.
The idea that both light and matter can exhibit both wave and particle properties.
It's a strange concept.
It is.
but it's essential to understanding the quantum world.
But how did this concept emerge, and what role did Heisenberg play in its development?
Well, around the same time that Heisenberg was developing matrix mechanics, another young physicist, Erwin Schrödinger,
Schrödinger.
came up with a completely different approach to quantum mechanics.
Hold on, two completely different approaches at the same time.
Yeah.
This is getting complicated.
It was a time of tremendous excitement and upheaval in physics.
I can imagine.
Schrödinger, building on the work of Louis de Broglie,
De Broglie.
focused on the wave aspect of matter.
The wave aspect.
Yeah, he developed an equation now famously known as the Schrödinger equation,
Okay.
which described the behavior of electrons not as particles,
Okay.
but as waves.
Waves. So instead of picturing tiny billiard balls whizzing around the nucleus,
Right.
we should be thinking of what ripples spreading out.
In a way, yes. Schrödinger's equation described these waves called wave functions,
Wave functions.
which spread out in space and contain all the information about the state of an electron.
So we have Heisenberg's matrix mechanics based on particles and observable quantities,
Right.
and Schrödinger's wave mechanics.
Two very different approaches.
Were these two theories rivals destined to clash?
There was definitely some tension.
Okay.
Heisenberg in particular was initially quite hostile to Schrödinger's wave mechanics.
Really?
He even referred to it as disgusting.
Oh, wow.
But there were also genuine conceptual differences.
Okay.
Heisenberg's matrix mechanics emphasized particles and observable quantities, while Schrödinger's wave mechanics seemed to prioritize the wave nature of matter.
So we have these two seemingly incompatible views of the quantum world.
Right.
What happened next?
Here's where Max Born, Heisenberg's mentor, once again played a crucial role.
Born again.
He had a remarkable ability to synthesize different ideas and see the bigger picture.
Yeah, he was a brilliant physicist in his own right.
Absolutely. He recognized the value of both matrix mechanics and wave mechanics.
Did he somehow manage to merge these two seemingly conflicting theories?
He did in a way by offering a completely new perspective on Schrödinger's wave function.
Okay.
He argued that the wave function itself didn't describe the electron's physical state directly,
Okay.
but rather contained information about the probability of finding the electron at a particular location.
Probability. You mean the electron doesn't have a definite position?
That's the radical idea.
Yeah.
According to Born, the wave function tells us the likelihood of finding an electron at a specific point in space.
Okay.
So we can't say for certain where the electron is, only the probability of finding it in various locations.
That's a huge departure from classical physics.
It is.
It's like saying a baseball doesn't have a definite trajectory until we actually observe it.
Right.
Just a cloud of possibilities.
Exactly. This probabilistic interpretation of the wave function became a cornerstone of quantum mechanics.
Okay.
But it was a bitter pill to swallow for many physicists, including Einstein, who famously declared, "God does not play dice."
Right. Einstein never fully embraced the strangeness of quantum mechanics.
He didn't.
So in essence, Born found a way to reconcile the wave-like behavior of electrons
Right.
with the particle-like observations we make in experiments.
Precisely. It's not that the electron is sometimes a wave and sometimes a particle.
Okay.
It's that it has properties of both. And the way it manifests depends on how we interact with it,
Okay.
how we observe it.
I think I'm starting to see why Heisenberg initially had a hard time accepting Schrödinger's wave mechanics.
Yeah,
It seemed to contradict his focus on observable quantities.
it did. And to make things even more complicated, Schrödinger soon demonstrated that his wave mechanics and Heisenberg's matrix mechanics were in fact mathematically equivalent.
Oh, wow.
They were just different ways of describing the same underlying reality.
That's incredible. It's like discovering that two seemingly different languages are actually just different ways of expressing the same ideas.
That's a great analogy. And it highlights the beauty and power of mathematics as a tool for understanding the universe.
So now we have this unified picture of quantum mechanics
Right.
with wave-particle duality at its core.
At its very heart.
But how did Heisenberg respond to this new understanding?
Well, he was still grappling with it.
Okay.
And where does the uncertainty principle fit into all of this?
Hmm.
That's the next chapter in our story.
Okay.
Heisenberg, still when somewhat resistant to the wave picture, went back to Copenhagen to work with Niels Bohr, who had become a kind of father figure for the emerging field of quantum mechanics.
Right, Bohr.
They engaged in intense discussions, often lasting late into the night,
I can imagine.
trying to grasp the philosophical and physical implications of this new theory.
It sounds like they were wrestling with some pretty profound questions.
They were questions that would shake the very foundations of physics and our understanding of reality itself.
Welcome back to our final dive into the life and legacy of Werner Heisenberg. Last time we left off with Heisenberg in Copenhagen, grappling with the profound implications of wave-particle duality and the probabilistic nature of quantum mechanics.
It was a time of intense intellectual ferment, with physicists struggling to make sense of a universe that no longer conformed to the neat deterministic laws of classical physics.
And it was during this time in 1927 that Heisenberg made another groundbreaking contribution, one that would forever change our understanding of the limits of knowledge, the uncertainty principle.
It's a concept that's often misunderstood. It's not just about limitations in our measuring instruments or the inherent clumsiness of our experiments.
Right.
It's about a fundamental property of nature, a deep-seated uncertainty woven into the fabric of reality itself.
So how did Heisenberg arrive at this profound insight? Was it a sudden flash of inspiration, or did it emerge slowly from his ongoing work?
Heisenberg's breakthrough came from his insistence on defining physical quantities operationally, meaning in terms of how they are measured.
Okay.
He realized that any measurement we make inevitably disturbs the system being measured.
So it's like we can't observe something without changing it in some way.
Exactly. And this isn't just a practical limitation, it's a fundamental principle.
Can you give me a concrete example? I'm trying to visualize this.
Sure. Imagine you're trying to measure the position of an electron. To see the electron, you need to shine light on it, right?
Right, that makes sense.
But light itself is made of photons, which carry momentum. When a photon hits the electron, it transfers some of its momentum, causing the electron's momentum to change.
So the very act of trying to pinpoint the electron's position by shining light on it inevitably alters its momentum.
Precisely. We can't know both with perfect accuracy.
So there's this inherent trade-off. The more accurately you measure the position, the less you know about the momentum, and vice versa.
That's the essence of Heisenberg's uncertainty principle. It's often expressed mathematically as xu h4, where xu the uncertainty in position, is the uncertainty in momentum, and h is Planck's constant. What this equation tells us is that the product of these uncertainties can never be smaller than a certain fundamental limit.
So it's not just a practical limitation, it's a fundamental law of nature.
Exactly. It's built into the very fabric of the quantum world. And this uncertainty isn't limited to position and momentum. The uncertainty principle applies to other pairs of complementary variables like energy and time.
So the more precisely we know the energy of a system, the less precisely we can know the time interval over which it has that energy.
You got it. The uncertainty principle is a profound concept with far-reaching implications. It tells us that at the quantum level, nature is inherently fuzzy, probabilistic. We can't pin down reality with the same kind of certainty that we're used to in the macroscopic world.
This must have been a radical shift in thinking for physicists at the time.
It was, and it still challenges our intuitions today. Einstein, for example, never fully accepted the probabilistic interpretation of quantum mechanics. He famously said, "God does not play dice."
But the experimental evidence has consistently supported the predictions of quantum mechanics, even the most paradoxical ones.
It has. Quantum mechanics has been one of the most successful scientific theories ever developed. It's the foundation of modern electronics, lasers, and even medical imaging.
It's amazing to think that Heisenberg developed matrix mechanics at just 23 years old, and the uncertainty principle just a few years later. What an incredible legacy for someone so young. But what happened to him after this tumultuous period of scientific discovery?
Heisenberg's life took a more complex turn as the political landscape in Germany shifted dramatically with the rise of the Nazi regime.
This was a dark time for Germany and for science. Many brilliant minds like Einstein and Born were forced to flee the country.
Heisenberg, however, chose to remain in Germany. He saw himself as a defender of theoretical physics, arguing for its importance in technological progress.
It's a decision that has been both praised and criticized. Some see it as an act of courage, while others view it as complicity with a brutal regime.
It's a complex issue, and historians continue to debate Heisenberg's motivations and actions during this period. What we do know is that he led a research group exploring the possibilities of nuclear energy during World War II.
There's been a lot of controversy surrounding his role in the German nuclear program. Did he actually try to build an atomic bomb for the Nazis?
That's a question that has haunted historians and scientists for decades. The evidence is ambiguous, and Heisenberg's own accounts are often contradictory. Some argue that he deliberately sabotaged the German effort, while others believe that he simply miscalculated the technical challenges.
We may never know for sure what Heisenberg's true intentions were, but his wartime activities remain a subject of intense scrutiny and debate.
After the war, Heisenberg played a key role in rebuilding German science. He became the director of the Max Planck Institute for Physics and helped establish CERN, the European Organization for Nuclear Research.
So, despite the controversies of the war years, he continued to make significant contributions to the scientific community.
He did. He also continued to explore the philosophical implications of quantum mechanics, the nature of reality, and the role of the observer.
It seems that Heisenberg was always driven by a deep curiosity, a desire to understand the fundamental nature of the universe and our place within it.
He was, and his work continues to inspire and challenge us today. His uncertainty principle remains a cornerstone of modern physics, and his philosophical musings on the observer effect have found new relevance in fields like quantum computing and information theory.
So what does this all mean? What are the key takeaways from our deep dive into the life and work of Werner Heisenberg?
Heisenberg's story is a testament to the transformative power of scientific curiosity, but also a reminder that science is not just a collection of facts and theories. It's a deeply human endeavor shaped by the personalities, passions, and even the flaws of those who pursue it.
Heisenberg's work revolutionized our understanding of the universe, but it also forced us to confront profound philosophical questions about the nature of reality knowledge and the limits of human understanding.
His legacy continues to inspire and challenge us, reminding us that there are still mysteries to be unraveled,
Yeah.
that the universe still holds secrets waiting to be discovered.
And perhaps the biggest question of all, one that Heisenberg himself grappled with. If the universe is fundamentally uncertain at its core, does that leave room for free will? It's a thought-provoking question to ponder as we conclude our deep dive into the fascinating world of Werner Heisenberg and quantum mechanics.